Today I will talk about grading virtual large and its applications. We will study how to grade virtual large and its applications. We will study how to compare virtual large by using this grading. And we will also study some family tree of virtual large. You know what is a virtual large? A virtual large can be regarded as a generalization of classical large. A virtual large diagram is not diagram allowed to have classical crossings and virtual crossing. Virtual crossing is denoted by a double point surrounded by a small circle like this one, and so a virtual large can have classical crossings and virtual crossing. Classical large can be distinguished by using Reidemeister movers in knot diagrams. These three movers are called Reidemeister movers, and if two knots are equivalent, then their diagrams can be rated by a finite sequence of Reidemeister movers illustrated in this figure. And similarly, we can also define a virtual version of Reidemeister movers for virtual large. So you can see that these three movers are similar to the Reidemeister movers, and in addition we consider another mover like this one, and these movers are called virtual movers. Then we can compare virtual large diagram by using virtual isotopy. A virtual isotopy is defined as a sequence of Reidemeister movers and virtual movers, and two knots are said to be virtually isotopic or equivalent if there is a virtual isotopy from one to the other. And a virtual large is defined as the virtual isotopy class of a virtual large diagram. Now we have a question about comparing virtual large. So in this paper we will study how to distinguish two given virtual large effectively. Actually there are many invariants of virtual large, and we can compare virtual large by using this invariant. But if two virtual large have many crossings, then although it is possible to compare them by using virtual large invariant, it can take much time to compare them, and in this case we want to simplify the problem by using some structure of virtual large diagram. Actually, we will study grading of virtual large in this talk. If two knots have many crossings, then if they have the same value for many knot invariants, then we will want to distinguish them by using another tool. So in this talk we will see some methods to compare some complicated virtual large. And based on the grading of virtual large, we will study how a family tree of virtual large. From the family tree, we can see a relationship between virtual large. About this talk, we will study some related history. First, Heinrich defined the sequence of virtual large invariants, which are virtual invariants of degree 1. In particular, a polynomial invariant of virtual large was introduced, and then there appears many generalizations of Heinrich's result. In particular, Chen introduced an odd-right polynomial by using Manteuff's poverty axiom, and Chen and Gao generalized the odd-right polynomial. In the paper, they used the coloring of Gauss diagram of virtual large. by analyzing the coloring, Kaufman introduced the affine index polynomial of virtual large, and it is easy to calculate the affine index polynomial, and it is useful to compare virtual large. But it has some shortage that you cannot compare many virtual large because it is a Bachelor invariant of degree 1. And so, for example, if two virtual large are related by a delta move, then they have the same value for the affine index polynomial. I have introduced the zero polynomial of virtual large, and this can distinguish some pairs of virtual large which cannot be distinguished by the affine index polynomial. Recently, Chang generalized this polynomial invariant of virtual large by using transcendental function invariant. Here is the abstract of our talk. By using the degree of crossing for each knot, we can define V and K, which is obtained from K by virtualizing some classical crossings, and then we will show that if two virtual large K1 and K2 are virtually isomorphic, then V and K1 and V sub and K2 are also virtually isomorphic. By using this process, we can compare two virtual large. Usually, V and K1 and V and K2 are much simpler than K1 and K2. And we also give us some examples showing that our grading is useful to distinguish virtual large, and we will also take a diagram of tree for virtual large. In this talk, all virtual large are assumed to be oriented. If we consider the crossing of a virtual large, then we can assign +1 or -1 for each crossing, which is called the sign of the crossing, which are defined as shown in this figure. And the rider of a knot diagram is defined as the sum of signs of all crossings of the virtual knot diagram. To define the degree of crossing, we will use a Gauss diagram. So now let's see what is a Gauss diagram. A virtual knot can be represented as a Gauss diagram and vice versa. If we have a virtual knot like this one, then we can see there are 3 classical crossings and 2 virtual crossings. If we take a starting point at here, and if we walk along the knot, then we can meet crossings C1, C2, and C3, and so on. And the crossings have crossing sign, and for each crossing we correspond a code with the crossing sign like this one. In this way, we can associate a Gauss diagram of a virtual knot. And conversely, if we have a Gauss diagram, then we can also construct a virtual knot diagram. So we can study virtual knot as the Gauss diagram of a knot, and to study about this, it is needed to analyze the light Meister movers. So if we represent the randomized moves and virtual isotopy in virtual diagram, we can represent it as a Gauss diagram as shown in this figure. The first move represents the first randomized move, and the second one expresses the second randomized move, and this move comes from the third randomized move. Here, epsilon may take plus or minus, which means the crossing sign of classical crossing. Now, we define the degree of crossing. We will identify a code and crossing, and if we have a code C of a Gauss diagram, then we count the number of positive code and negative codes intersecting C, and if we consider the positive code and negative code intersecting C from left to right, then we denote it R sub plus, and similarly we denote the R minus to be the negative code intersecting C from left to right. Similarly, we also define R sub plus and R sub minus. So R plus means the number of positive codes intersecting C from right to left. And then we define the degree, which is denoted by d over C, defined as shown in this formula. So dc is defined as R sub plus minus R sub minus minus R sub plus plus R sub minus. For example, if we consider such a Gauss diagram which have 4 codes, in particular if we consider C1, then we meet C2, C3 and C4. C2 crosses C1 from left to right, so C2 contributes -1 to the degree of C1, and C3 crosses C1 from right to left, so C3 contributes -1 to the degree of C1, and C4 crosses C1 from left to right, and its sign is minus, so C4 contributes -1 to the degree of C1. In this way, we can see that the degree of C1 is -3, and similarly, we can calculate the degree of C2, C3, C4 in this way. Now, we study some notations which will be used in this talk. From now on, CK will denote the set of all crossings in K, and we consider a subset of CK denoted by C sub nk, where n can be any natural number. C sub nk is defined as the collection of crossings, so that the degree of C is divisor of n. And Vnk, or k of n, will denote the virtual lot obtained by virtualizing all crossings in ck minus C sub nk. So if n is 2, then truth k means the virtual lot obtained by virtualizing all other crossings. And inductively, we will define k of n1 and m as the breadth of nm, k n1 and n minus 1. In this way, for each natural number, and we can consider Vnk, and if n1, nm are integers, we can also get virtual lot defined in this way. So let's see what Kaufman and Chen have done for invariance of virtual lots by using the degree. The alpha index polynomial, which is denoted by p sub kt, is defined by using this formula. So it is defined as the sum of sign multiplied by t to the degree of c minus 1. And This is an invariant of virtual latch, and in particular, it vanishes for all virtual latch with more than one crossing. So it is a very sharp invariant of degree 1. Actually, the affine index polynomial is not so strong to compare virtual latch. So if two virtual latch are related by delta move, then they cannot be distinguished. And similarly, if we consider 2x move, which is defined as shown in this figure, where epsilon can be positive or negative, if we call this move 2x move, then we can show that PKT is invariant under the 2x move. So PKT is relatively easy to calculate the invariant for virtual latch, but it's not so strong to compare virtual latch. Now we will show that V and K are invariant of a virtual latch. At first, we will see that V and K is invariant for the first randomized move. If K1 and Ka2 are virtual latch related by a first randomized move, then we will show that VNK1 and VNK2 are equivalent, so they are actually related by a first randomized move for any natural number n. Let's briefly see the proof for this lemma. If D is a crossing of K1 distinct from C, then since the code up here does not intersect with any other crossing, we can see that the degree of D in GK1 and GK2 are the same. And if we consider this code C, then the degree of C is 0, and so C belongs to CNK1, and we can see that C appeared at VNK1, but C can be removed by using the first randomized move. So we can see that Vn of K1 and Vn of K2 are virtually isotopy. Similarly, we can show that if two virtual latch K1 and K2 are related by a second randomized move, then they are also related by a second randomized move. The second randomized move can be shown in this figure. Then the most complicated one for the proof is the case for the third randomized move. If we consider a third randomized move as shown in this figure, we will show that VNK1 and VNK2 are virtually isotopy. Okay, let's see the proof of the theorem. If K1 and K2 are related by a third randomized move, and D is a crossing of K1 distinct from C1, C2, and C3, then you can easily see that the crossing C1, C2, and C3 does not affect the degree of D, and so D is an element of C and K1 if and only if the corresponding crossing D prime belongs to C and K2. And we should note that the degree of C1 can be calculated as a sum of DC2 and DC3. You can see that in this figure, the degree of C1 is 0, and the degree of C2 is -1, and the degree of C3 is +1. And if there are more codes between this part, then we can also show that the equation is valid. And we can also show that the degree of Ci is equal to that of Ci prime. And so we can see that the number of elements in C1, C2, C3 intersection C and K1 can be 1 or 3. So we should analyze these two cases. At first, if we consider this case, then we can see that actually V sub n K1 and V sub n K2 are equivalent, because if the class is C1, then C2, C3 will be removed in this virtual lot, and C2 prime and C3 prime will be removed in this diagram. Similarly, if we consider this case, then VNK1 and VNK2 are related by the third right minus move, and so VNK1 and VNK2 are equivalent. Now we have proved the theorem that if K1 and K2 are virtually isotropic, then V sub n K1 and V sub n K2 are also virtually isotropic for each natural number, and by repeatedly applying this result to virtual lots K1 and K2, we can get this correlate, saying that if N1 and M are natural numbers and K1 and K2 are equivalent, then these two virtual lots are also equivalent. Now we study about V and K. If K is a virtual lot whose Gauss diagram is given in this figure, then by adding two codes at here and two codes at here, you can see that K is equivalent to V3 K prime. More generally, we can prove this theorem, saying that for any virtual lot K and any integer n, there exists a virtual lot K prime, such that K is virtually isotropic to Vn K prime. And we can also show the following theorem by considering the connected sum of virtual lots. If the greatest common divisor of n1 and n2 are neither n1 nor n2, then we can show that there exists a virtual lot K prime, so that Ki is equivalent to V sub n I K prime for each I. Here is an example of distinguishing virtual lots. Actually, K cannot be distinguished from the trivial knot just by using the affine index polynomial. But if we consider V sub 2k, then we can show that V2k is non-trivial, and so K must be non-trivial. And here is grade 3 of virtual lot. At this diagram, the letter number denotes the degree of code, so K2 is obtained from K by removing all codes whose degree is odd. So we get a diagram like this one, and similarly K3 is obtained from this diagram by removing all codes whose degree is not a multiple of 3, and so we get a diagram like this one, and so on. So we can see a relationship between virtual lots. Thank you very much.